We'll discuss today the rational and irrational numbers. We denote the set of all real numbers by R, double R, we call this one. We represent the set of all real numbers, in a real line with O as origin is 0 and along positive right hand part 1, 2, 3 positive x-axis representing the positive real numbers and along this axis representing the negative real numbers. A real number is of two types. One is Q, the set of all rational numbers, and another is Q complement, QC, the set of all irrational numbers. What are the rational numbers? Rational numbers are like 1, 1 by 2, minus 3 by 2, dot dot dot. What are the irrational numbers? Root 2, root 3, pi, e, etc. like this. From this we can see that definition of the complement, Q complement equal to R minus Q. That is the real numbers which is not the rational numbers. And we know that for the complement property, Q intersection Q complement equal to 5. This means that a real number x, any real number x, cannot be both rational and irrational numbers. That is, for any arbitrary x picked from this real line, it is either rational number or it is an irrational number. Now, what is the definition of real number? How we define a real number? As its structure shows that it is a very well behaved or well structured. What is that structure? That structure has been used for the definition of the set of all real numbers. We define a rational number in the form P by Q, where PQ belongs to Z, where Z is the set of all integers and denominator is not equal to 0. Because something divided by 0 is not defined. So any number of the form P by Q, where PQ are integers and Q greater than 0 is defined to be a real number. Now how we define the rational number? As the definition, Q complement is a set of all irrational numbers. This means that it is not rational. We define a rational number, a real number which is not a rational number is called an irrational number. So what is important thing is that a irrational number is also a real number, a rational number is also a real number. Any number, any real number cannot be simultaneously rational number and irrational number. We will demonstrate an example. We first prove that the number root 2 is not a rational number. How we can prove? We will prove this by the method of contradiction. Suppose we consider root 2 is not a rational number. Then is a rational number. Root 2 is a rational number. Since it is a rational number, it can be expressed in the form root 2 equal to P by Q, where PQ belongs to Z, the set of all integers, Q not equal to 0. And we consider this GCD of PQ equal to 1. This means that P and Q are prime to each other. Because if they have any common factor, we can cut this one to get a number in the form P by Q such that the GCD of PQ is equal to 1. So squaring both sides, we get P square equal to TQ square. This implies P square is an even number. And we know that if square is even number, the number itself an even number. So P is even, this means P equal to 2K, where K is an integer, K belongs to Z. Therefore, putting this value of p in this equation, that is 2k whole square equal to 2q square, we have q square equal to 2k square. This means that q square is an even number. Similarly, q square is an even number, and so q is even number. Therefore, what we conclude from here that p and q are not prime to each other because they have a common factor at least 2 and other may be there. So p and q are not prime to each other. But we have assumed here is a prime to each other. So we arrive in a contradiction. What is that contradiction? Contradiction is that what we have assumed, that root 2 is a rational number. It's a contradictory statement means that which is not true. What is the complementary statement of this statement? That is root 2 is a rational number. Its contradictory statement is that root 2 is not a rational number. So from this example, what we conclude that root 2 is not a rational number. If root 2 is not a rational number, then what is the type of number root 2 can be? For this, we go to the geometry. In the geometry, we find that, suppose this is our real axis. We take this way, is 1 unit, so one way represents 1. With the same length, we draw a perpendicular line AB. Where AB is perpendicular to the x-axis. We can apply Pythagoras theorem. By Pythagoras theorem, OB equal to root 2. And taking a compass with this root 2 as radius, we draw a circle. And this circle cuts the real line at P. And we know that any point on the real line is a real number. Since this root 2 value cutting the point at P, this means that the OP represents the value root 2. This means that root 2 is a real number. So if it is not rational number, the other option is that it is irrational number. This means that is when a number is not rational number, it is irrational number. Of course, the number must be a real number. We now give the decimal representation of rational number and irrational number. Rational numbers can be represented as a terminal decimal number, recurring decimal point number, or both. Some rational numbers have both the representations, terminating as well as the recurring. We can express. What is terminating? Example, 1 by 2, we know this is 0.5. It is terminating because after that there is no values. This means that we put them as 0. What is the recurring? 1 by 3 is equal to 0.33333 and so on. And we write mathematically as 0.3 recurring by this dot or sometime by giving bar. In some author, you just said this is 0.3 bar. Or another recurring number, suppose 0.786, 786, 786 and dot dot dot. We have given a number, decimal number by this representation. This means that this is 0.7 dot, 8 dot, 6 dot, or sometimes we write this as 0.786 bar. In some author, they use this notation. How we represent a irrational number in decimal system, that is if we express in decimal number system. And as definition of the irrational number, we studied that, we give that a number is not rational number. This means that decimal representation of an irrational number is the complement of this part. What is complement of this part? That is neither terminating nor recurring. What actually it does mean? The neither terminating nor recurring. This means that we represent a number after decimal point. There are infinite number of terms. This means it is not terminating, but this infinite number of digits will follow any definite rule or recurring rule. In fact, recurring rule. Definite rule means that in this case you can see that this is 01, 1.01, 001, 0001, after that 401, then 501 and so on. If you go continue, you can find some rule, but this is not the recurring rule. Recurring rule means that a periodic number, a finite number of digits will occur after a finite number of steps with a rule, with a period. The number you can see that pi, we also mentioned, pi is an irrational number. You can see its decimal representation. That is 3.14159265. There are infinite number of digits we can find out, but you cannot find any recurring decimal. Similarly, E, the number E, its value is 2.7182818284, and its value similarly after decimal point, it has infinite number of digits, infinite number of digits, and the digits 7182818284 is not a recurring number. Hence, pi and E are irrational numbers. So what is that we get? A decimal representation of rational number is either terminating or recurring or both. We sometimes represent for some rational numbers both the terminating or in terms of recurring. For irrational number, the decimal representation is neither terminating nor recurring. These are the examples. We now give two examples on conversion from recurring to fractional form. In example 1, let x is equal to 0.4999 and so on. We can write this as 0.49 dot 9 recurring 999 multiply x by 10. See, this is point, one place is there, we multiply it by 10. This means we get 4.999 and so on. Again we multiply 10 by this number. So we get, this is 100x is equal to 49.999. If we subtract, the decimal part will go off. The process is that, trick is that, you find the decimal numbers, the decimal part is same for such a multiplication by 10 or 100 or 1000 and so on. Once you get the decimal part is same, then you can able to subtract to get the fractional form or p by q form. So if we subtract, we will get 45, x is equal to 45 by 90, this is equal to half. Also this half, also another representation, that is 0.5, which is a terminating one. Example 2, let x is equal to 1.27 bar, this means 27, 27, 27 and so on. We multiply 100, 127.2727, this fractional part now comes equal. So we are in a position to subtract. 100x minus x equal to 127 minus 1 equal to 126. Therefore x is equal to 126 by 99. Cutting by 9 both sides. This is 11, this is 14. So the number is 14 by 11. Likewise, any recurring number can be converted to the form p by q. Many examples can be cited, and we stop our lecture today. I think you have enjoyed our lecture. Thank you very much.